Automotive systems. There are 2 or 3 main objectives for people who create automotive devices. Increasing the miles per gallon performance and reducing the harmful emissions are the top 2 priorities, while running the vehicle on water alone is the aim of a few people. The first 2 objectives are readily achievable, but running a vehicle on water alone is not going to happen for almost everybody. This idea is peddled by con artists who sell worthless plans, claiming that these will run a vehicle on water for anybody who wants to construct these simple devices. This is just not true. You are welcome to download the HydroStar and hydrogen plans free from http://www.freeenergyinfo.com/p61.pdf and http://www.freeenergyinfo.com/p62.pdf. However, most experienced people looking at these plans are convinced that they could not possibly produce enough hydrogen-oxygen gas mix to run an engine. While I have never heard of anyone, anywhere, ever getting an engine to run on these plans, the present-day science of water is so inadequate, that I am not in a position to be certain that they could not work, and so I am just highly doubtful as to them being viable devices. Just before getting on to explain the construction details of practical systems, let me put the running of an engine on water alone in its proper context. The internal combustion engine which you own has an efficiency less than 50%. This means that at least half of the energy available from the fuel which you use is wasted and does not produce any useful mechanical output power. In many cases, that percentage can be as high as 90% wasted, but let's be generous and assume that your particular engine is especially good and manages 50% efficiency. The main way of running an engine with water as the only fuel involves splitting water into hydrogen and oxygen and then burning those gases to power the engine. To be self-sustaining, the splitting of the water has to be done by the electrics of the vehicle, and that means that the efficiency of the water splitting has to be more than 200% efficient. That just doesn't happen with simple systems, so please forget the notion of building some device in your garage with a couple of hours work and waving goodbye to filling stations forever. It ain't going to happen. Just to set the record straight, it is possible to appear to run a car on water alone, but the difficulty level is about the same as building a rocket capable of going into orbit, something well beyond the capabilities of most people, including me. This document does tell you how it can be done, but please understand that it calls for exceptional skills, very considerable expenditure and a great deal of patience, so for the time being, please forget about it. What can be done quite readily and at low cost, is to construct a device which will raise the efficiency of your engine. This is done by feeding a hydrogen/oxygen gas mix, called HHO gas, into your engine along with the air which is drawn in to make the engine run. A device of this type is called a booster as it boosts the fuel burn, extracting a greater percentage of the fuel's available energy. An important side effect of this improvement in the burn quality of the fuel is the fact that unburned fuel no longer gets pushed out of the exhaust as harmful emissions. Another effect is that the engine has greater pulling power and runs smoother. Inside your engine, carbon deposits will have built up from previous unboosted running, and these deposits get burnt away when you use a booster, and that internal cleaning extends the engine life. Some people worry about the fact that burning HHO gas produces water, and they imagine this water causing rusting inside the engine. What they don't realize is that the ordinary fuel used in the engine is a hydrocarbon, which is a compound of hydrogen and carbon, and that fuel actually splits up to form hydrogen which the engine burns. Actually, it is the carbon part of the hydrocarbon fuel which is the problem, producing carbon dioxide, carbon monoxide, and physical carbon deposits inside the engine. A normal fuel burn produces water anyway, but you don't get rusting inside the engine as the temperature there is so high that any water is in the form of steam or vapor which dry out completely when the engine is switched off. Adding a small amount of HHO gas has no adverse effects at all. This document describes different types of booster. Let me stress that each engine is different, and it depends on how inefficient the engine is to begin with, what sort of MPG improvement is likely to be produced by a booster. Just to make sure that you understand what is involved, A booster is a simple container which holds a set of plates submerged in water which probably has an additive to make the water conduct electrical current better. A pipe from the top of the container feeds the gas into the air filter of the vehicle, via one or two simple safety devices. Adding this gas causes a major improvement in the quality of the fuel burn inside the engine and cuts harmful emission to near zero. As a consequence of this, it is possible to reduce the amount of fossil fuel being sent to the engine, which is not something which should be done if HHO gas is not being added, as the engine is liable to overheat and some valve damage could occur. It is a completely different matter if HHO gas is being added. However, all recent engine designs have an electronic control unit, ECU, which controls the amount of fuel being sent to the engine. The ECU accepts input signals from an oxygen sensor placed in the exhaust stream, and often a second sensor after the catalytic converter to make sure that the catalytic converter has not failed. Unfortunately, the much improved exhaust caused by the better fuel burn caused by the HHO gas, causes the ECU to think that the engine fuel-air mix must be too low, and so it pumps in more fuel in an effort to compensate. Ideally, this can be dealt with by adding a circuit board which adjusts the signal coming from the oxygen sensor so that it is correct for the improved fuel burn. Details of how to do this are in a companion document. So, to recap, the only practical device which you can build yourself and use to improve automotive performance is a booster. Using a booster improves the efficiency of the fuel burn inside your engine, and that results in more power, better torque, smoother running and vastly improved exhaust emissions. If the ECU is not adjusted or its input signal not controlled, the MPG figures may actually get slightly lower due to unwanted excess fuel being pumped into the engine. If a control circuit is used to correct this ECU error, then MPG gains will be produced. So, what MPG gains can be expected? The worst I have ever heard of was 8%, which is very rare. The lowest likely gain is 20%. Typical gains are in the 25% to 35% bracket. Not particularly unusual is 35% to 60%, while gains up to 100% and over have been achieved, but they are rare. A realistic expectation would be a 33% gain. This chapter is divided up into the following sections. 1. Simple DC boosters, using a 12-volt electrical input. 2. Advanced DC boosters using much higher DC voltages. 3. Water splitters which use pulsed electrical signals to change water into HHO gas. 4. Running engines without fossil fuels. 5. Other useful devices. One thing which needs to be understood. Caution, a booster is not a toy. If you make and use one of these, you do so entirely at your own risk. Neither the designer of the booster, the author of this document, or the provider of the internet display are in any way liable should you suffer any loss or damage through your own actions. While it is believed to be entirely safe to make and use a properly built booster, provided that the safety instructions shown in this document are followed, it is stressed that the responsibility for doing this is yours and yours alone. Simple DC boosters. It is important that you understand the basic principles of electrolysis if you are to be successful in building and operating a booster, or alternatively, buying and operating a booster. A DC booster operates on direct current, which is the sort of electrical power delivered by a car battery. The method is very simple in basic outline. Two metal plates are placed in water and an electric current is passed between the plates. This causes the water to break down into a mixture of hydrogen gas and oxygen gas, the two components used in the space shuttle. The greater the flow of current, the larger the volume of gas which will be produced. The arrangement is like this. Remembering that the result of doing this is to produce fuel for the space shuttle, you should avoid doing this indoors and letting the gas produced by the process collect on the ceiling. There are many videos on the web where people act in a dangerous manner and perform electrolysis indoors using a container which is open at the top as shown above. Please don't do that, as it is highly dangerous. It is not a party popper which pushes the space shuttle into space. If you were to collect a cupful of HHO gas and light it, the resulting ignition would probably damage your hearing permanently, so don't do it under any circumstances. Just like the fact that a very useful chainsaw is a dangerous device which needs to be treated with respect, so too, please understand that the very useful HHO gas mix contains a lot of energy and so needs to be treated with respect. This style of electrolysis of water was investigated by the very talented and meticulous experimenter Michael Faraday. He presented his results in a very technical and scientific format which are not understood by most ordinary people. But in simple terms, he tells us that the amount of HHO gas produced is proportional to the current flowing through the water, so to increase the rate of gas production, you need to increase the current flow. Also, he found that the optimum voltage between the two electrode plates is 1.24 volts. This sounds a bit technical, but it is a highly useful piece of information. In the arrangement shown above, 12 volts is being connected across two plates in water. Faraday tells us that only 1.24 volts of that 12 volts will go to make HHO gas and the remaining 10.76 volts will act as an electric kettle and just heat the water, eventually producing steam. As we want to make HHO gas and not steam, this is bad news for us. What it does tell us is that if you choose to do it that way, then only 10% of the power taken by the booster actually makes HHO gas and a massive 90% is wasted as heat. We really don't want a low electrical efficiency like that. One way around the problem is to use two cells like this. This arrangement uses our 1.24 volts twice while the 12 volts stays unchanged and so the electrical efficiency goes up to 20% and the heat loss drops to 80%. That is quite an improvement, but even more important is the fact that twice as much HHO gas is now produced, so we have doubled the electrical efficiency and doubled the gas output, giving a result which is 4 times better than before. We could go one step further and use 3 cells like this. This time we are using 3 of our 1.24 volt sections and this gives us an electrical efficiency of 30% and 3 times the amount of gas, making the system 9 times more effective. This is definitely going in the right direction, so how far can we take it when using a 12-volt battery? When we use the construction materials which years of testing has shown to be particularly effective, there is a small voltage drop across the metal plates, which means that the very best voltage for each cell is about 2 volts and so with a 12-volt battery, 6 cells is about the best combination, and that gives us an electrical efficiency of 62% and 6 times as much gas, which is 37 times better than using a single cell, and the wasted electrical power drops down from 90% to 38%, which is about as good as we can get. Of course, it would not be practical to have 6 boxes each as large as a car battery as we would never manage to fit them into most vehicles. Perhaps we could just put all the plates inside a single box. Unfortunately, if we do that, a good deal of the electric current would flow around the plates and not make much gas at all. A top view of this arrangement is shown here. Most current skips the middle plates. This is a disaster for us as now we will not get your 6 times the gas production or our massively reduced heating. Thankfully, there is a very simple fix for this problem, and that is to divide the box up into 6 watertight compartments using thin partitions like this. This gives us back our high efficiency by blocking the current flow past the plates and forcing the current to flow through the plates, producing gas between every pair of plates. In passing, if this booster were to be powered by the electrics of a vehicle, then the voltage, although called 12 volts, will actually be almost 14 volts when the engine is running, so that the 12-volt battery will get charged. This would allow us to use 7 cells inside our electrolyzer, rather than the 6 cells shown above, and that would give us 7 times the gas volume that a single pair of plates would give. Some people prefer 6 cells, and others, 7 cells. The choice is up to the person constructing the unit. We have been discussing the methods of increasing the gas production and reducing the wasted energy, but please don't assume that the objective is to make large volumes of HHO gas. It has been found that with many vehicle engines, very good performance gains can be had with a HHO gas production rate of less than 1 liter per minute, LPM. Flow rates of as little as 0.5 to 0.7 LPM are frequently very effective. Remember, the HHO gas from a booster is being used as an igniter for the regular fuel used by the engine and not as an additional fuel. The big advantage of an efficient booster design is that you can produce the wanted volume of gas using a much lower current, and so, a lesser extra load on the engine. Admittedly, there is not much additional engine load needed by a booster, but we should reduce the extra amount by intelligent design. In the discussion above, the battery has been shown connected directly across the booster or electrolyzer. This should never be done as there is no protection against a short circuit caused by a loose wire or whatever. There should be a fuse or a circuit breaker as the first thing connected to the battery. Circuit breakers are available from any electrician's supply outlet as they are used in the fuse box in homes, to provide protection for each lighting circuit and each power socket circuit. They are not expensive as they are manufactured in very large volumes. They are also available on eBay. The circuit breaker is wired like this. A common design, rated at 32 amps, looks like this. Some would-be constructors feel that some aspects of the construction are too difficult for them. Here are some suggestions which might make construction more straightforward. Constructing a 7-cell housing is not difficult. Pieces are cut out for 2 sides, 1 base, 1 lid and 6 absolutely identical partitions. These partitions must be exactly the same so that there is no tendency for leaks to develop. If you decide to use the bent plate system of electrodes shown on the next few pages, then drill the bolt holes in the partitions before assembling them. The bottom piece is the same length as the sides, and it is the width of the partitions plus twice the thickness of the material being used to build the housing. If acrylic plastic is being used for the construction, then the supplier can also provide an adhesive which effectively welds the pieces together, making the different pieces appear to have been made from a single piece. The case would be assembled like this. Here, the partitions are fixed in place one at a time, and finally, the second side is attached and will mate exactly as the partitions and ends are all exactly the same width. A simple construction for the lid is to glue and screw a strip all the way around the top of the unit and have the lid overlap the sides as shown here. A gasket, perhaps of flexible PVC, placed between the sides and the lid would assist in making a good seal when the lid is bolted down. The gas outlet pipe is located in the center of the lid, which is a position which is not affected if the unit is tilted when the vehicle is on a steep hill. Years of testing have shown that a really good choice of material for the electrode plates is 316 L-grade stainless steel. However, it is very difficult to connect those plates electrically inside the cells as you need to use stainless steel wire to make the connections, and bolted connections are really not suitable. That leaves welding the wires to the plates, and welding stainless steel is not something which a beginner can do properly as it is much more difficult than welding mild steel. There is a good alternative, and that is to arrange the plate material so that no wire connections are needed. While this 6-cell design may look a little complicated to a quick glance, it is really a very simple construction. Each of the plates used in the central cells is just this shape. The plate shapes shown above are arranged so that there is access to the bolts from above and they can be reached by a spanner and held steady while the other nut is being tightened. Unless you are skilled in bending plates, I suggest that you use stainless steel mesh for the plates. It works very well, can be readily cut using tin snips or any similar tool, and it can be bent into shape by the home constructor using simple tools, a vise, a piece of angle iron, a small piece of mild steel sheet, a hammer, etc. You will find a skip outside any metal fabrication shop where scrap pieces are tossed for recycling. There will be offcuts of various sizes of angle iron and all sorts of other small sections of sheet and strip. They are in the skip mainly to get rid of them as the fabrication business gets paid almost nothing for them. You can use some of these pieces to shape your booster plates, and if you feel bad about costing the business about a penny, then by all means put them back in the skip afterwards. If you clamp your plate between 2 angle irons in a vise, then careful, repeated gently tapping with a hammer close to the bend location, will produce a very clean and neat bend in the plate. The bent sheet can then be clamped between two steel strips and a sharp U-shaped bend produced by tapping with a hammer, again, along the line of the required bend. The thickness of the steel bar on the inside of the bend has to be the exact width of the required gap between the finished plate faces. This is not particularly difficult to arrange, as 3 mm, 3.5 mm, 4 mm, 5 mm and 6 mm are common thicknesses used in steel fabrication, and they can be combined to give almost any required gap. There are many varieties of stainless steel mesh. The style and thickness are not at all critical, but you need to choose a type which is reasonably stiff and which will hold its shape well after it is bent. This style might be a good choice. Your local steel supplier probably has some types on hand and can let you see how flexible a particular variety is. The shape shown above is for a 3-plate per cell design where there are 2 active plate faces. Ideally, you want 2 to 4 square inches of plate area per amp of current flowing through the cell, because that gives very long electrode life and minimum heating due to the plates. This style of construction is reasonably easy to assemble, as the 2 bolts which pass through the partitions and which hold the plates rigidly in place, can be accessed from above, 2 spanners being used to lock them tight. Lock nuts are optional. If you feel that your particular mesh might be a little too flexible, or if you think that the bolts might eventually loosen, then you can attach 2, or more, separator insulating pieces, plastic washers, plastic bolts, cable ties or whatever to one of the plate faces. These will hold the plates apart even if they were to become loose. They also help to maintain the gap between the plates. This gap has to be a compromise, because the closer the plates are together, the better the gas production, but the more difficult it is for the bubbles to break away from the plates and flow to the surface, and if they don't do that, then they block off some of the plate area and prevent further gas production from that part of the plate, as the electrolyte no longer touches the plate there. A popular choice of gap is 1/8 inch, which is 3 mm, as that is a good compromise spacing. Circular spacers would look like this. If the current is low enough, an even more simple shape which has just a single pair of active plate surfaces per cell, can be used as shown here. Any of these designs can be 6-cell or 7-cell, and the plates can be constructed without outside help. You will notice that the electrical connections at each end of the booster are submerged to make sure that a loose connection can't cause a spark and ignite the HHO gas in the top of the housing. There should be a gasket washer on the inside to prevent any leakage of the electrolyte past the clamping bolt. If you want to use 3 active plate pairs in each cell, then the plate shape could be like this. The electrolyte is a mix of water and an additive to allows more current to flow through the liquid. Most of the substances which people think of to use to make an electrolyte are most unsuitable, producing dangerous gases, damaging the surfaces of the plates and giving uneven electrolysis and currents which are difficult to control. These include salt, battery acid and baking soda, and I strongly recommend that you do not use any of these. What is needed is a substance which does not get used up during electrolysis and which does not damage the plates even after years of use. There are 2 very suitable substances for this: sodium hydroxide, also called lye or caustic soda. In the USA, this is available in Lowe's stores, being sold as Robic heavy-duty crystal drain opener. The chemical formula for it is NaOH. One other substance which is even better is potassium hydroxide or caustic potash, chemical formula KOH, which can be got from soap-making supply shops found on the web. Both NaOH and KOH are very caustic materials, and they need to be handled with considerable care. Bob Boyce of the USA is one of the most experienced people in the construction and use of boosters of different designs. He has kindly shared the following information on how to stay safe when mixing and using these chemicals. He says, these materials are highly caustic, and so they need to be handled carefully and kept away from contact with skin, and even more importantly, eyes. If any splashes come in contact with you, it is very important indeed that the affected area be rinsed off immediately with large amounts of running water, and if necessary, the use of vinegar, which is acidic and so will neutralize the caustic liquid. When making up a solution, you add small amounts of the hydroxide to distilled water held in a container. The container must not be glass, as most glass is not high enough quality to be a suitable material in which to mix the electrolyte. The hydroxide itself should always be stored in a sturdy, airtight container which is clearly labeled danger. Potassium, or sodium, hydroxide. Keep the container in a safe place, where it can't be reached by children, pets or people who won't take any notice of the label. If your supply of hydroxide is delivered in a strong plastic bag, then once you open the bag, you should transfer all of its contents to sturdy, airtight, plastic storage containers, which you can open and close without any risk of spilling the contents. Hardware stores sell large plastic buckets with airtight lids that can be used for this purpose. When working with dry hydroxide flakes or granules, wear safety goggles, rubber gloves, a long-sleeved shirt, socks and long trousers. Also, don't wear your favorite clothes when handling hydroxide solution, as it is not the best thing to get on clothes. It is also no harm to wear a face mask which covers your mouth and nose. If you are mixing solid hydroxide with water, always add the hydroxide to the water, and not the other way round, and use a plastic container for the mixing, preferably one which has twice the capacity of the finished mixture. The mixing should be done in a well-ventilated area which is not drafty, as air currents can blow the dry hydroxide around. When mixing the electrolyte, never use warm water. The water should be cool because the chemical reaction between the water and the hydroxide generates a good deal of heat. If possible, place the mixing container in a larger container filled with cold water, as that will help to keep the temperature down, and if your mixture should boil over, it will contain the spillage. Add only a small amount of hydroxide at a time, stirring continuously, and if you stop stirring for any reason, put the lids back on all containers. If, in spite of all precautions, you get some hydroxide solution on your skin, wash it off with plenty of cold running water and apply some vinegar to the skin. Vinegar is acidic, and will help balance out the alkalinity of the hydroxide. You can use lemon juice if you don't have vinegar to hand, but it is always a good idea to have a bottle of vinegar handy. The concentration of the electrolyte is a very important factor. Generally speaking, the more concentrated the electrolyte, the greater the current and the larger the volume of HHO gas produced. However, there are three major factors to consider. 1. The resistance to current flow through the metal electrode plates. 2. The resistance to current flow between the metal plates and the electrolyte. 3. The resistance to current flow through the electrolyte itself. In a good electrolyzer design like those shown above, the design itself is about as good as a DC booster can get, but understanding each of these areas of power loss is important for the best possible performance. We were taught in school that metals conduct electricity, but what was probably not mentioned was the fact that some metals such as stainless steel are quite poor conductors of electricity, and that is why electrical cables are made with copper wires and not steel wires. This is how the current flow occurs with our electrolyzer plates. The fact that we have folds and bends in our plates has no significant effect on the current flow. Resistance to current flow through the metal electrode plates is something which can't be overcome easily and economically, and so has to be accepted as an overhead. Generally speaking, the heating from this source is low and not a matter of major concern, but we provide a large amount of plate area to reduce this component of power loss as much as is practical. Resistance to flow between the electrode and the electrolyte is an entirely different matter, and major improvements can be made in this area. After extensive testing, Bob Boyce discovered that a very considerable improvement can be made if a catalytic layer is developed on the active plate surface. Details of how this can be done are given later in the companion D9.pdf document as part of the description of Bob's electrolyzer. Resistance to flow through the electrolyte itself can be minimized by using the best catalyst at its optimum concentration. When using sodium hydroxide, the optimum concentration is 20% by weight. As 1 cubic centimeter of water weighs 1 gram, 1 liter of water weighs 1 kilogram. But, if 20%, 200 grams, of this kilogram is to be made up of sodium hydroxide, then the remaining water can only weigh 800 grams and so will be only 800 cubic centimeters in volume. So, to make up a 20% by weight mix of sodium hydroxide and distilled water, the 200 grams of sodium hydroxide are added, very slowly and carefully, as explained above by Bob, to just 800 cubic centimeters of cool distilled water, and the volume of electrolyte produced will be about 800 cubic centimeters. When potassium hydroxide is being used, the optimum concentration is 28% by weight, and so, 280 grams of potassium hydroxide are added, very slowly and carefully, as explained above by Bob, to just 720 cubic centimeters of cold distilled water. Both of these electrolytes have a freezing point well below that of water, and this can be a very useful feature for people who live in places which have very cold winters. Another factor which affects current flow through the electrolyte is the distance which the current has to flow through the electrolyte. The greater the distance, the greater the resistance. Reducing the gap between the plates to a minimum improves the efficiency. However, practical factors come into play here, as bubbles need sufficient space to escape between the plates, and a good working compromise is a spacing of 3 mm, which is 1/8 of an inch. However, there is a problem with using the optimum concentration of electrolyte, and that is the current flow caused by the greatly improved electrolyte is likely to be far more than we want. To deal with this, we can use an electronic circuit called a pulse width modulator, or PWM, circuit. These are often sold as DC motor speed controllers, and if you buy one, then pick one which can handle 30 amps of current. A pulse width modulator circuit operates in a very simple way. It switches the current to the electrolyzer on and off many times every second. The current is controlled by how long, in any 1 second, the current is on, compared to how long it is off. For example, if the on time is twice as long as the off time, 66%, then the average current flow will be much greater than if the on time were only half as long as the off time, 33%. When using a pulse width modulator controller, it is normal to place its control knob on or near the dashboard and to mount a simple low-cost ammeter beside it so that the driver can raise or lower the current flow as is considered necessary. The arrangement is like this. There is a more sophisticated circuit controller called a constant current circuit, and that allows you to select the current you want, and the circuit then holds the current at your set value at all times. However, this type of circuit is not readily available for sale, although some outlets are preparing to offer them. Some of the most simple boosters don't use a pulse width modulator circuit because they control the current flow through the booster by making the concentration of the electrolyte very low so that the resistance to current flow through the electrolyte chokes off the current and holds it down to the desired level. This, of course, is far less efficient, and the resistance in the electrolyte causes heating, which in turn, is an operational problem which needs careful handling by the user. The advantage is that the system appears to be more simple. Feeding HHO gas to an engine. When using a booster of any design, you need to realize that HHO gas is highly energetic. If it wasn't, it would not be able to do its job of improving the explosions inside your engine. HHO gas needs to be treated with respect and caution. It is important to make sure that it goes into the engine and nowhere else. It is also important that it gets ignited inside the engine and nowhere else. To make these things happen, a number of common sense steps need to be taken. Firstly, the booster must not make HHO gas when the engine is not running. The best way to arrange this is to switch off the current going to the booster when the engine is not running. It is not sufficient to just have a manually operated on-off switch, as it is almost certain that switching off will be forgotten one day. Instead, the electrical supply to the booster is routed through the ignition switch of the vehicle. That way, when the engine is turned off and the ignition key removed, it is certain that the booster is turned off as well. so as not to put too much current load on the ignition switch, and to allow for the possibility of the ignition switch being on when the engine is not running. Instead of wiring the booster directly to the switch, it is better to wire a standard automotive relay across the oil pressure unit and let the relay carry the booster current. The oil pressure drops when the engine stops running, and so this will also power down the booster. An extra safety feature is to allow for the, very unlikely, possibility of an electrical short circuit occurring in the booster or its wiring. This is done by putting a fuse or contact breaker between the battery and the new circuitry as shown in this diagram. If you choose to use a contact breaker, then a light-emitting diode, LED, with a current limiting resistor of say, 680 ohms in series with it, can be wired directly across the contacts of the circuit breaker. The LED can be mounted on the dashboard. As the contacts are normally closed, they short-circuit the LED and so no light shows. If the circuit breaker is tripped, then the LED will light up to show that the circuit breaker has operated. The current through the LED is so low that the electrolyzer is effectively switched off when the contact breaker opens. This is not a necessary feature, merely an optional extra. A good source for general components needed in building boosters is the Hydrogen Garage in the USA. Website, http://stores.homestead.com/hydrogengarage/storefront.bak. A very important safety item for any booster is the bubbler, which is just a simple container with some water in it. The bubbler has the gas coming in at the bottom and bubbling up through the water. The gas collects above the water surface and is then drawn into the engine through an outlet pipe above the water surface. To prevent water being drawn into the booster when the booster is off for any length of time and the pressure inside it reduces, a one-way valve is placed in the pipe between the booster and the bubbler. If the engine happens to backfire, then the bubbler blocks the flame from passing back through the pipe and igniting the gas being produced in the booster. A bubbler is a very simple, very cheap and very sensible thing to install. It also removes any traces of electrolyte fumes from the gas before it is drawn into the engine. In practice, it is a very good idea to have two bubblers, one close to the booster and one close to the engine. The second bubbler makes sure that every last trace of electrolyte fumes are washed out of the HHO gas before it enters the engine. There are various ways to make a good bubbler. In general, you are aimed at having a 5-inch, 125 mm, depth of water through which the HHO gas must pass before it leaves the bubbler. It is recommended that a bubbler is built inside a strong container such as this one. These strong containers are generally sold as water filters. They can be adapted to become bubblers without any major work being done on them. At this point, we need to consider the mechanism for moving the HHO gas out of the booster and into the engine. It is generally a good idea to position the gas take-off pipe in the center of the lid so that if the booster gets tilted due to the vehicle operating on a sloped surface, then the surface level of the liquid remains unchanged underneath the gas pipe. A common mistake is to use a gas pipe which has a small diameter. If you take a length of plastic pipe of a 1/4 inch diameter, 6 mm, and try blowing through it, you will be surprised at how difficult it is to blow through. There is no need to give your booster that problem, so I suggest that you select a gas pipe of 1/2 inch, 12 mm, or so. If in doubt as to how suitable a pipe is, then try blowing through a sample length of it. If you can blow through it without the slightest difficulty, then it is good enough for your booster. One other thing is how to deal with splashes and the spray from bubbles bursting at the surface of the electrolyte. You want some device which will prevent any spray or splashes caused by the vehicle going over a very rough road, from entering the gas pipe and being drawn out of the booster along with the HHO gas. Various methods have been used and it is very much a matter of personal choice as to how you decide to deal with the issue. One method is to use a piece of suitable material across the end of the pipe. This is generally called anti-slosh material because of the job which it does. The material needs to let the gas pass freely through it but prevent any liquid getting through it. Plastic pot scrubbers as a possible material as they have an interlocking mesh of small flat strands. The gas can flow around and through the many strands, but splashes which go in a straight line will hit the strands and drip back into the booster again. Another possible device is one or more baffles which will catch the liquid but let the gas pass freely by. Or the HHO gas produced by a DC booster of this type contains about 30% monatomic hydrogen, which means that 30% of the hydrogen is in the form of single atoms of hydrogen and not combined hydrogen pairs of atoms. The monatomic form is about 4 times more energetic than the combined form, and so it takes up a greater volume inside the booster housing. If the booster is left turned off for a long period of time, then these single hydrogen atoms will eventually bump into each other and combine to form the less energetic diatomic form of the gas. As this takes up less space inside the booster, the pressure inside the booster drops, and this has been known to suck water out of the bubbler back into the booster. We don't want this to happen, as it dilutes our carefully measured electrolyte concentration and it can make the bubbler ineffective due to lack of water. To deal with this, a one-way valve is put between the booster and the bubbler, positioned so that it does not allow flow back into the booster. In very cold climates, a 28% by weight potassium hydroxide electrolyte will not freeze until -40 degrees Celsius. It is more difficult to stop the bubblers freezing. While it is possible to have equipment which unplugs and can be taken indoors overnight, an alternative is to use alcohol or paraffin, kerosene, instead of water, and they generally do not freeze and their fumes are not harmful to an engine. The bubbler design is not difficult. Ideally, you want a very large number of small bubbles to be formed and float upwards through the water. This is because it gives the best connection between the gas and the water, and so can do a really good job of washing any traces of hydroxide vapor out of the HHO gas before it gets fed to the engine. Small bubbles are also better separated from each other, and so there is no real chance of a flame passing through the water, where large bubbles might merge together and form a column of gas as they rise to the surface. In this good bubbler design, the pipe which feeds the HHO gas into the bubbler is bent into an L shape. The end of the pipe is blocked off, and many small holes are drilled in the horizontal section of the pipe. Only a few holes are seen in this diagram, but there will be a large number in the actual construction. Like the booster itself, the gas outlet pipe needs to be protected from splashes of water caused by the vehicle going over a bump. It is very important to make sure that water is not drawn into the engine along with the gas, so anti-slosh material or one or more baffles are used to prevent this happening. So the overall protection for the gas flow is where the first bubbler is close to the booster and the second one is placed close to the engine. Once in a while, the water from the first bubbler can be used to top up the water inside the booster so that any traces of hydroxide which may have reached the bubbler are returned to the booster, keeping its electrolyte concentration exactly right and making sure that the water in the bubbler is always fresh. There is one final item which is an optional extra. Some people like to add a gas pressure switch. If, for any reason, the pressure starts to rise, say that the outlet pipe became blocked, then the pressure switch would disconnect the electrical supply and stop the pressure rising any further. One decision which has to be made is the rate of HHO gas production, which is the best for you. Most people seem to think that the larger the volume of HHO gas the better. That is not necessarily true, because a very effective use of the gas is to make it act as an igniter for the engine's normal fuel, and very satisfactory results have been achieved with HHO gas flow rates in the range of 0.4 to 0.7 liters per minute. You control the rate of gas production by controlling the current, either by the concentration of the electrolyte or by adjusting the current flow using an electronic circuit. Each liter of water produces about 1750 liters of HHO gas, so you can estimate the length of time the booster can operate on 1 liter of water. If, for example, your booster is producing 0.7 liters of gas per minute, then it will produce 1750 liters in 2500 minutes or 41 hours 40 minutes. As the booster only operates when you are driving, you are looking at 41 hours of driving time, and if you drive about 2 hours per day, it would take 3 weeks to use 1 liter of water. The internal dimensions of your booster allow you to calculate how far the electrolyte level will drop if 1 liter of water is taken out of it. Generally speaking, it is normally considered that topping up the booster with water by hand every so often is a perfectly good method of operation. The booster design described above has a good electrolyte capacity in each cell, and so topping up with water should not be a major task. As tap water and well water have a good deal of dissolved solids in them, when the water is taken away by electrolysis, these solids drop out of solution and fall to the bottom of the housing, and coat the plates with a layer of unwanted material. For this reason, life is so much easier if distilled water is used for making electrolyte and for topping up the booster after use. It is possible to have an automatic water supply for your booster, even though that is probably overkill for such a simple device. If you decide to do that, then you need a water supply nozzle for each of your 6 or 7 cells. It is not necessary for the electrolyte level to be exactly the same in each cell, but you would normally have them at roughly the same height. Your automated water supply could be like this: nozzle, one-way valve, water pump, water supply nozzles, plastic tube, manifold pipe, one-way valve, water pump. A point which might not be immediately obvious is that because the gas pressure inside the booster is probably about 5 pounds per square inch, psi, once the water pump stops pumping, it is possible for the gas pressure to push out the remaining water in the inlet pipes and escape through the body of the pump. To prevent this, an ordinary one-way valve is put in the water supply pipe to prevent flow back towards the pump. Up to now, the HHO gas feed to the engine has just been indicated in a vague way in spite of the connection point being important. With most engines, the HHO gas should be fed into the air filter where it mixes well and is fully dispersed inside the air being drawn into the engine. You sometimes see diagrams which show the connection point being close to the engine intake manifold. This is not a good idea because the lowered pressure there causes reduced pressure inside the booster, which in turn produces more unwanted hot water vapor, so stick with feeding the gas into the air filter. If there is a supercharger on the engine, then feed the HHO gas into the low pressure side of the supercharger. The SMAX booster. The style of booster described above has the advantages of high electrical efficiency, easy construction, very few specialist parts, and a large electrolyte volume per cell. There are many other very successful booster designs, which have very different forms of construction. One of these is the SMAX booster, where electrical cover plates are clamped together and placed inside a length of plastic pipe. The advantages of this design are the very simple construction, compact size, reasonable performance, and the fact that you can buy one ready-made if you want to. You can download a copy of the construction details free from http://www.freeenergyinfo.com/smac.pdf. The electrical efficiency of this design is lowered a bit because only a single body of electrolyte is used, and so current can bypass the plates. The overall performance is a respectable 1.3 lpm for 20 amps, though you may wish to lower the current and settle for about half that rate of HHO gas production. The construction of a 5 lpm version is at www.youtube.com. The Hotsabi booster. Another design which is very easy to build is the Hotsabi booster, which is a single threaded rod inside a length of plastic pipe with a stainless steel inner lining. It has the lowest possible electrical efficiency, being just a single cell with the full vehicle voltage connected directly across it, but in spite of that, its performance in actual on-the-road use has been remarkable, with a reported 50% improvement on a 5-liter capacity engine. This excellent performance is probably due to the design having a steam trap which removes the hot water vapor produced by the excessive heating caused by having only a single cell with so much voltage across it. Remember, 90% of the power supplied to this booster design goes in heating the electrolyte. As the designer of this booster has freely shared his design, the free construction plans can be downloaded from http://www.freeenergydevices.com/hotsabi.pdf. Controlling the oxygen sensor. When an MPG Improving device such as an electrolyzer is fitted to a vehicle, the result does not always produce better MPG. Figures. Older vehicles which are fitted with a carburetor will see an immediate improvement. This is not the case for more recent vehicles which come with computer control of the fuel sent to the engine. When an electrolyzer is attached to the engine, it causes the fuel burn inside the cylinders to be greatly improved, with a corresponding improvement in engine performance. Unfortunately, the fuel computer is expecting the same amount of unburned oxygen to come out of the engine, and when it doesn't detect it, the computer increases the fuel flow rate into the engine in an attempt to get back to its normal, inefficient method of running. That action cancels the MPG improvement produced by the electrolyzer unless something is done to adjust the operation of the computer. In the most simple terms, most vehicles which have an electronic control unit, ECU, to control the fuel flow into the engine, are fitted with one of two types of exhaust sensor. The majority have a narrow band sensor while the remainder have a wide band sensor. The ideal mix of air to fuel is considered to be 14.7 to 1. A narrow band sensor only responds to mixtures from about 14.2 to 1 through 14.9 to 1. The sensor operates by comparing the amount of oxygen in the exhaust gas to the amount of oxygen in the air outside the vehicle, and it generates an output voltage which moves rapidly between 0.2 volts where the mixture is too lean, and 0.8 volts when it passes below the 14.7 to 1 air-fuel mix point where the mixture is too rich, as indicated by the graph shown below. The ECU increases the fuel feed when the signal level is 0.2 volts and decreases it when the signal voltage is 0.8 volts. This causes the signal voltage to switch regularly from high to low and back to high again as the computer attempts to match the amount of too lean time to the amount of too rich time. A simple control circuit board can be added to alter the sensor signal and nudge the fuel computer into producing slightly better air/fuel mixes. Unfortunately, there is a severe downside to doing this. If, for any reason, the fuel mix is set too high for an extended period, then the excess fuel being burnt in the catalytic converter can raise the temperature there high enough to melt the internal components of the converter. On the other hand, if the circuit board is switched to a mix which is too lean, then the engine temperature can be pushed high enough to damage the valves, which is an expensive mistake. Over-lean running can occur at different speeds and loads. Johansson recommends that if any device for making the mix leaner is fitted to the vehicle, then the following procedure should be carried out. Buy a Type K thermocouple with a 3-inch stainless steel threaded shank, custom built by Thermex southwest of San Diego. This temperature sensor can measure temperatures up to 1800 degrees Fahrenheit, 980 degrees centigrade. Mount the thermocouple on the exhaust pipe by drilling and tapping the pipe close to the exhaust manifold, just next to the flange gasket. Take a cable from the thermocouple into the driver's area and use a multimeter to show the temperature. Drive the vehicle long enough to reach normal running temperature and then drive at full speed on a highway. Note the temperature reading at this speed. When a leaner mix is used, make sure that the temperature reading under exactly the same conditions does not exceed 180 degrees Fahrenheit, 100 degrees centigrade, above the pre-modification temperature. David Andrusik recommends an alternative method of avoiding engine damage through over-lean fuel-air mixtures, namely, replacing the narrow-band oxygen sensor with a wide-band sensor and controller. A wide-band oxygen sensor reads a very wide range of air-fuel ratios, from about 9 to 1 through 28 to 1. A normal car engine can run from about 10 to 1, very rich, to about 17.5 to 1, pretty lean. Maximum engine power is developed at a mix ratio of about 12.5 to 1. Complete fuel combustion takes place with a mix of about 14.7 to 1, while the mix which gives minimum exhaust emissions is slightly leaner than that. Unlike narrow-band sensors, wide-band sensors need their own controller in order to function. There are many of these units being offered for sale for retrofitting to existing vehicles which have just narrow-band oxygen sensor systems. David's personal recommendation is the Innovate Motorsports LC, one which is small, and uses the very reasonably priced LSU-4 sensor. This wideband controller can be programmed. Most controllers have the ability to output two signals, the wideband signal suitable for running to a gauge or new ECU, plus a synthesized narrowband signal which can feed an existing ECU. The trick is to install a wideband sensor, with the LC-1 controller and then reprogram it to shift the narrowband output to achieve a leaner mix as shown here. This system allows you to set the narrowband toggle point very precisely on an exact chosen air-fuel ratio. This is something which it is nearly impossible to do accurately with a circuit board which just shifts a narrowband oxygen signal, as you just do not know what the air-fuel ratio really is with a narrowband sensor. However, for anyone who wants to try adding a circuit board to alter a narrowband sensor signal to produce a leaner mix on a vehicle, the following description may be of help. It is possible to buy a ready-made circuit board, although using a completely different operating technique, from the very reputable Eagle Research, via their website, http://www.eagleresearch.com/products/pfuels.html, where the relevant item is shown like this. This unit generates a small voltage, using a 555 timer chip as an oscillator, rectifying the output to give a small adjustable voltage which is then added to whatever voltage is being generated by the oxygen sensor. This voltage is adjusted at installation time and is then left permanently at that setting. Eagle Research also offer for sale a booklet which shows you how to build this unit from scratch if you would prefer to do that. If you wish to use a circuit board with a narrowband oxygen sensor, then please be aware that there are several versions of this type of sensor. The version is indicated by the number of connecting wires. Those with one wire, where the wire carries the signal and the case is ground, 0 volts. Those with two wires, where one wire carries the signal and the other wire is ground. Those with three wires, where two, typically slightly thicker, wires are for a sensor heater, and one for the signal while the case is ground. Those with four wires, the most common on current model cars, where there are two, slightly heavier, for the sensor heater, one for the signal, and one for the signal ground. Sensors with 5 wires are normally wideband devices. Look in the engine compartment and locate the oxygen sensor. If you have difficulty in finding it, get a copy of the Climber or Haynes maintenance manual for your vehicle, as that will show you the position. We need to identify the sensor wire which carries the control signal to the fuel control computer. To do this, make sure that the car is switched off, then, for 3 and 4 wire sensors, disconnect the oxygen sensor wiring harness. Set a multimeter to a DC voltage measurement range of at least 15 volts. Turn on the ignition and probe the socket looking for the 2 wires that provide 12 volts. These are the heater wires, so make a note of which they are. Shut the ignition off, and reconnect the oxygen sensor. The 2 remaining wires can now be treated the same as the wires from a 2-wire sensor, one will carry the sensor signal and one will be the signal ground. For a single-wire sensor, the signal ground will be the engine block. Jesper Ingerslev points out that the Ford Mustang built since 1996 has 2 oxygen sensors per catalytic converter, one before the converter and one after. Some other vehicles also have this arrangement. With a vehicle of this type, the circuit board described here should be attached to the sensor closest to the engine. Find a convenient place along the wires. Don't cut these wires, you will cut the sensor wire here at a later time, but not now. Instead, strip back a small amount of the insulation on each wire. Be careful to avoid the wires short-circuiting to each other or to the body of the vehicle. Connect the DC voltmeter to the wires, the non-heater wires. Start the engine and watch the meter readings. When the engine is warmed up, if the oxygen sensor is performing as it should, that is, no engine check lights on, the voltage on the meter should begin toggling between a low value near 0 volts and a high value of about 1 volt. If the meter reading is going negative, then reverse the meter leads. The black multimeter lead is connected to the signal ground, 0 volts, and the red lead will be connected to the wire which carries the signal from the sensor. Connect a piece of insulated wire to the stripped point of the sensor wire and take the wire to the input of your mixture controller circuit board. Connect a second insulated wire between the signal ground wire, or in the case of a one-wire sensor, the engine block, and the circuit board 0 volts line. Insulate all of the stripped cables to prevent any possibility of a short circuit. Plastic covered cables going to circuit board. Remove a small piece of insulation and join the new cable to the original wire without cutting the original wire. Wrap each joint in insulation tape. More specific detail. However, the situation is by no means a simple one which allows a single simple adaptation which will work on every vehicle for many years. Leigh Pearson has been investigating this situation in depth for 3 years along with a friend who is an electronics engineer. Having built and tested EFIEs, the oxygen sensor circuit shown below, several versions of map controllers, coolant/air temperature hacks, professional systems, etc., and discovered that many vehicle ECUs, electronic control units, learned to adapt to the new conditions and return to the highly inefficient excess fuel injection condition. This return to the original fuel injection is different for each design of ECU and there are many different designs. Leigh says, to understand the solution, first you have to understand the dilemma with all the other ECU control tricks. The EFIEs, map adjusters, temp hacks etc. do get good results for a short time, and then the performance deteriorates again. Why should this be? It is because the ECU learns to deal with the new situation with them in place. This is because the ECU knows that the feedback from most of its controls and sensors are not linear, nor should they be. All of the electronics and adjustment methods used by the hydrogen on-demand people are linear, and that is not an adequate way to deal with the problem. For example, we may add a couple of 100 millivolts to the oxygen, lambda, sensor signal in order to return an unduly rich signal to the ECU, and so make it respond with a lower level of fuel injection. This makes the ECU think that the air-fuel ratio is say, 15, 1 or 20, 1. Now the mass air maps are all wrong. We need to show less air so that the ECU adds less fuel in order to match the fuel trims. We now need to adjust the ignition timing to take advantage of this combustion change. The problem is that all the EFIEs, map adjusters, and attempts at changing timing by manipulating air temp are a static fixed offset, producing just a single change. An air-fuel ratio of 20:1 is not appropriate under moderate or heavy acceleration when you don't, and usually can't, add enough hydroxy gas to allow for these conditions. A set 15% to 20% leaner setting across the entire fuel map is not appropriate at all loads and engine speeds. Adding 50 to 75 degrees F to the air temp is not appropriate when the outside air is already at 110 degrees F. The ECU knows this and makes appropriate changes to its long-term settings, and so it cancels out the changes which our electronic additions have made. While it may be okay for an experimenter and mechanic with all the tools at his disposal to play with these techniques, and retune his engines every week or so in order to get great mileage, it is not realistic to expect the average person to do this. The cost in equipment alone would undermine any fuel savings. Also, most people don't even change their oil at appropriate intervals. This was my train of thought, says Leigh. As I pondered a solution, and began searching, my search was for a control solution which could firstly, alter the airflow readings, lambda readings, and ignition timing, and secondly, respond to changes in engine speed and engine load. To my surprise, I found several products already on the market which are capable of doing this, and which have been available for quite some time. People in the engine tuning industry have been using them for years. They are custom programmable, piggyback chips. Several companies make them, and while most do not advertise O2, lambda, sensor control, many are quite capable of altering it. We became a distributor for one brand which seemed to be the best fit for our purposes, and we began testing. The results are perfect. We started with an 2002 Saturn SL. The average MPG for this car started at 26 miles per gallon, highway and city combined. We installed the chip, tested several tuning methods, and found the one which worked best. The car now averages 44 to 46 miles per gallon. This is not special grandma driving to try and coax a few extra miles per gallon. This is a courier vehicle for a local printer, and it is driven daily like it was stolen. We have all the same benefits of increased torque, pulling power, better throttle response, etc. The car has been driven around for 3 months now with our programmed chip installed, and it achieves the mid-40s in MPG all of the time. There are no code changes needed, no startup problems, no driving problems of any kind whatsoever. If you weren't told, you would never know that hydroxy gas was being added, except for the fact that you can go over 500 miles on a single tank of fuel. The only problem is that this is definitely not a do-it-yourself solution. You need a laptop computer with proprietary software to tune the chip, and the scanning and diagnostic equipment to know when you have it tuned correctly. However, I have thought of a do-it-yourself solution. It still requires you to buy a few electronic kits, and you need a lot of know-how, but we are circumventing a highly sophisticated control architecture, so anyone who thinks it will be easy, is delusional. The main item is a digital fuel adjuster or DFA kit from J-Car Electronics based in Australia. Their website is http://www.jcar.com. The adjuster kit number is KC5385, and you have to have the hand controller to program it. That kit number is KC5386. The adjuster doesn't have an enclosure supplied, but the controller does. You need one controller and 2 adjusters. The controller can be reused to program multiple adjusters. Once you have the kits, it will take several days of soldering to build them, and it is definitely not a beginner's first time project. After the 2 adjusters and the controller have been built, the first one is wired into the MAP sensor signal as shown in the instructions guide. Next, the second DFA is used on the oxygen sensor signal. If there are 2 oxygen sensors, then the DFA is wired through the common ground for the upstream sensors only. This places the voltage offsets in tandem, which makes it unnecessary to use 2 DFAs, or EFIEs for that matter, for lambda control. Now control has been established over fuel maps, and a lambda control which is responsive to engine load has been achieved. I believe that these kits also come with an option to make them responsive to RPM. For ignition timing, the temperature offsets will probably still be necessary, but now you have a fuel control which, if tuned properly, the ECU will not learn its way around. I have found that the maps for lambda control are very simple. Tune for the leanest air-fuel ratio appropriate at very low loads, and richen up a bit in increments as the load increases. As you get close to full throttle, but before you switch to open loop operation, your lambda offset should be 0, the stock setting. To tune the airflow or fuel maps, watch the OBD2 scan gauge, and decrease the map signal so that your short-term fuel trim, STFT on a scanner, is no greater than about 7% at each load interval. Drive for about 20 minutes, and check that your long-term fuel trim, LTFT, never goes beyond the 7s. Either. Now the ECU cannot see your changes because the fuel map and lambda readings agree at every load range. The J-Car kits are not as sophisticated as the chipsets, but they are about 20% of the cost, if you want to put the time and effort into them. The adjuster itself simply adds to, or subtracts from, whatever voltage runs across them, and it can be set to change that offset value in correspondence to whatever voltage value is present at the signal input pin. You would of course put your TPS signal to the signal input pin. The device itself is very versatile, and could be used for many different applications. If you wanted to use one to control a pulse width modulator attached to a cell, then that would be possible and it would provide a variable gas rate that responds to changes in engine load. I hope you can put this to good use, and feel free to spread the word around. Perhaps you know someone who could build a similar device or give us a schematic to build one, after looking at a J-car kit. The only drawback to the kits is that RPM sampling gets a little complex, and while I don't think it is absolutely necessary, it would be beneficial. Although the kits have only 125 data points between the closed and fully open throttle settings, and do not interpolate between data points, they seem to work very well. The professional chipsets have 96,000 data points between CT, closed throttle, and WAT, wide open throttle, and they do logically interpolate between set data points. The professional chipsets run about $650 USD programmed and installed. I think that the more is better hydroxy gas idea that a lot of people are stuck in, is seriously flawed. There is definitely a point of diminishing returns. I tune most systems to deliver about 1 LPM. The lower the amperage you can do this at, of course the better. I have found that not only does it take more amperage to produce higher volumes at a less effective rate of return, but it does not add much to the efficiency of the boosting. With the cells which I build I get 1 LPM of hydroxy gas at about 8 to 10 amps. I'm using direct DC with a 5-cell, 6-plate array, similar to a SMAX booster, but with better plate isolation in the bath. We've spent thousands developing fancier, and slightly more efficient cells. We've used PWMs to get better production, and be able to attenuate gas production with duty cycle. We had a really advanced system. Then I applied Occam's razor to it. We can make enough gas to support ultra-lean combustion above fairly low load conditions, so what good is it to be able to decrease when you barely make enough already? The pulse width modulation does help, and is relatively inexpensive, so we kept that component if the customer wants, but we don't change the duty cycle. The 6-plate SMAX style cell works fine. It is small, easy to build, and is efficient enough for the production we need. Engine control was the biggest issue. I can get great mileage with just a little hydroxy gas, if I can control what fuel table the ECU looks at every load range, and RPM. The problem with EFIEs, and MAP adjusters is that they tell the computer to look at inappropriate fuel tables at higher load ranges. The ECU picks up on that, adjusts its long-term fuel trims, and goes back to an unmodified state. If I can make the ECU look at very lean tables at cruise, and then more or less unmodified tables at higher loads, it never sees the trick. Since we only make enough hydroxy gas to affect low loads anyway, that is all I need to be concerned with. You could think of it as an ultra-lean cruise mode. When you aren't at low cruise you aren't changing anything. When you are cruising you are running at a very lean air-fuel ratio. So far, it works great. The super fancy system that used a PWM with a duty cycle controlled by our chip, and made up to 3 LPM at 20 amps would have cost over $2,500 just for the parts, and equipment to cover production cost, and turn a profit, and it only gained us about 10% efficiency. The system we are working on now should be less than $1,500 as a turnkey system. Our little Saturn just came back at 88 miles per gallon on a carefully driven run with this system. It typically gets high 40s to mid 50s in MPG under normal driving conditions. I have tried adding just 0.6 LPM or so, and letting the ECU trim out to compensate. This has given me mixed results. Sometimes I can get 25% to 30% reduction in consumption, and sometimes it makes no difference at all. It has a lot to do with the ECU's programming, and the driver's habits. I don't really know why it doesn't work all the time. Theoretically it should. The hydroxy gas makes the petrol more volatile, so you should be getting more energy per gram of fuel. That should correlate to higher exhaust gas temperatures, and the ECU should see that and take away some fuel, but sometimes it does just the opposite. The ECU sees a lean condition due to increased exhaust gas temperature at the manifold, and lower temperature at the catalytic converter, and so it richens up the air-fuel mix. Another possible option that I have not explored would be an EFIE designed to change its output to a set voltage controlled by the vehicle's throttle position sensor. The challenge here is that it is not a linear change. The steps between load sites would not be equal. They would need to be able to be manually set for what the application needed. The DFAs allow you to do this, and can add voltage just like an EFIE. You can use one DFA for MAF control, and one for oxygen sensor control. So even with a modified EFIE you would need a DFA or something similar to provide nonlinear MAF control. You can contact Leigh at lespearson, at hotmail.commander. Construction. If you wish to build an oxygen sensor controller circuit, then here is a suggestion as to how you might do it. This description assumes very little knowledge on the part of the reader, so I offer my apologies to those of you who are already expert in these matters. There are many different ways to design and construct any electronic circuit, and each electronics expert will have his own preferred way. In my opinion, the way shown here is the easiest for a newcomer to understand and build with the minimum of tools and materials. This circuit can be constructed on a printed circuit board, or it can be built on a simple single-sided strip board as shown here. Strip board, often called Vero board, has copper strips attached to one side of the board. The copper strips can be broken where it is convenient for building the circuit. Component leads are cut to length, cleaned, inserted from the side of the board which does not have the copper strips, and the leads attached to the copper strips using a solder joint. Soldering is not a difficult skill to learn, and the method is described later in this document. When all of the components have been attached to the strip board and the circuit tested, then the board is mounted in a small plastic case as shown here. Insulating posts can be made from short pieces of plastic rod with a hole drilled through its length. The mounting bolt can self-tap into a hole drilled in the case, if the hole is slightly smaller than the diameter of the bolt. Threads. Alternatively, the holes can be drilled slightly larger and the bolt heads located outside the case with nuts used to hold the board in place. This style of mounting holds the circuit board securely in place and gives some clearance between the board and the case. You will need building equipment, namely, a soldering iron, a 12-volt power supply such as a battery pack, and an accurate digital voltmeter for this project. If the 12-volt supply is a main-powered unit, then it needs to be a well-filtered, voltage-stabilized unit. Lastly, you will need a variable voltage source that can go from 0 to 1 volt to imitate the output from the vehicle's oxygen sensor when testing the completed circuit board. This is simple enough to make, using a resistor and a variable resistor. A series of components will be needed for the circuit itself. These can be bought from a number of different suppliers, and the ordering details are shown later in this document. Shown above is a resistor. The value of the resistor is indicated by a set of 3 color bands at one end of the body. The reason for doing this rather than just writing the value on the resistor, is that when the resistor is soldered in place, its value can be read from any angle and from any side. The component list shows the color bands for each of the resistors used in this circuit. If you want more information on basic electronics, then read the electronics tutorial, which can be found at http://www.freeenergyinfo.com/chapter12.pdf. Other components which you will be using look like this. The MPSA14 and the BC327 devices are transistors. They each have a collector, a base and an emitter wire coming out of them. Please notice that the two packages are not identical, and take care that the right wire is placed in the correct hole in the strip board before soldering it in place. The 1N4007 diode has a ring marked at one end of the body. The ring indicates the flat bar across the symbol as shown on the circuit diagram, and in that way it identifies which way round the diode is placed on the strip board. The light-emitting diode, the LED, will be familiar to most people as it is used so extensively in equipment of all types. The toggle switch has 6 contacts, 3 on each side. The center contact is connected to one of the 2 outer contacts on its side, which one, depends on the position of the switch lever. The 2 capacitors, which are called condensers in very old literature, look quite different from each other. The electrolytic capacitor has its plus wire marked on the body of the capacitor, while the ceramic has such a small value that it does not matter which way round it is connected. The main component of the circuit is an integrated circuit or chip. This is a tiny package containing a whole electronic circuit inside it, resistors, capacitors, diodes, whatever. Integrated circuit chips generally look like this. A very common version of this package has 2 rows of 7 pins each, and it goes by the grandiose name of dual in-line, which just means that there are 2 rows of pins, each row having the pins in a straight line. In our particular circuit, the chip has 18 pins, in 2 rows of 9. Now to the circuit itself. If you find it hard to follow, then take a look at the electronics tutorial on the website, as it shows the circuit diagram symbol for each component and explains how each device works. The circuit contains 3 capacitors, 8 resistors, 2 diodes, 1 LED, 1 IC chip, 2 transistors, 1 toggle switch, and 2 types of component not yet described, namely, 2 preset resistors and 1 rotary switch. The preset resistor is very small and is adjusted using a flat-bladed screwdriver. It is used for making an adjustable setting, which is then left unchanged for a long time. The rotary switch has a central contact which is connected to a row of outer contacts in turn when the shaft is rotated from position to position. The switch shaft is made of plastic and so can easily be cut to the length needed to make a neat installation, and the knob is locked in place by tightening its grub screw against the flat face of the shaft, although some knobs are designed just to push tightly onto the shaft. There is a wide range of knob styles which can be used with this switch, so the choice of knob is dictated by personal taste. This is the circuit diagram. Electronic circuits are normally read from left to right, so we will look at the circuit that way. The first components are the 100 microfarad, 35-volt electrolytic capacitor with the tiny 100 NF capacitor across it. These are put there to help iron out any variations in the voltage supply. The BZX85C Zener diode is a 24-volt type, and it protects the integrated circuit from voltage spikes coming along the 12-volt line from other equipment in the vehicle, preventing the circuit from being fed more than 24 volts for even a fraction of a second, as that would damage the integrated circuit. The next item is the on-off dashboard switch. When switched to its off position as shown here, the connection from the oxygen sensor is passed straight through to the vehicle's fuel computer, bypassing the circuit board completely. This switch allows the whole circuit to be switched off should you want to do this for any reason. In its on position, as shown in the circuit diagram, the varying voltage signal coming from the oxygen sensor is passed into the circuit, and the output voltage from the circuit is passed back to the fuel computer, instead of the original sensor voltage. This allows the circuit to manipulate the voltage sent to the fuel computer. The next set of components, 4 resistors, 1 ceramic capacitor and 1 preset resistor, shown here, are needed to feed the incoming sensor voltage to the integrated circuit chip, and make the chip operate in the way that we want. The chip manufacturer allows more than one way for the chip to work. You can just ignore these components for now, just understand why they are there. The integrated circuit chip has 10 outputs, coming out through pins 1 and 10 through 18 inclusive. If the input voltage coming from the oxygen sensor is low, then all of these 10 outputs will have low voltages on them. When the input voltage rises a little, the voltage on pin 10 suddenly rises to a high value, while the other output pins still have low voltages. If the input voltage rises a little higher, then suddenly the voltage on pin 11 rises to a high value. At this point, both pin 10 and pin 11 have high voltage on them, and the other 8 output pins remain at low voltage. If the input voltage rises a little higher again, then suddenly the voltage on pin 12 rises to a high value. At this point, pin 10, pin 11 and pin 12 all have high voltage on them and the other 7 output pins remain at low voltage. The same thing happens to each of the 10 output pins, with the voltage on pin 1 being the last to get a high voltage on it. The circuit is arranged so that pin 10 provides the output signal for the richest air-fuel mixture for the vehicle, and the mix gets progressively leaner as the output on pins 11, 12, etc. are selected to be fed to the fuel computer. As there is the possibility of engine damage if the fuel mix is too lean, only 6 of the outputs are taken on into the circuit. However, if the engine is being fed hydroxy gas from an electrolyzer to improve both the miles per gallon performance and reduce emissions to zero, then it is likely that the engine will run cooler than before and engine damage is most unlikely to occur. It is quite safe to leave the remaining output pins of the integrated circuit chip unconnected. However, if this unit is to be used with the nitrogen hydroxide cell described in the D18.pdf document, then it is quite safe to connect pins 16, 17, 18 and 1 and set the rotary switch to 10 positions. The output pin to be used by the remainder of the circuit is selected by the rotary switch mounted on the dashboard. A standard single-pole rotary wafer switch has 12 positions, but the switch operation can be restricted to any lesser number of positions by placing the end-stop lug of the switch just after the last switch position required. This lug comes as standard, fits around the switch shaft like a washer, and is held in place when the locking nut is tightened on the shaft to hold the switch in place. The lug projects down into the switch mechanism and forms an end stop to prevent the switch shaft being turned any further. With 6 switch positions, the circuit provides 5 levels of leaner air-fuel mix which can be selected. This should be more than adequate for all practical purposes. The next section of the circuit is the BC327 transistor amplifier stage, which provides the output current for the fuel computer. Here, the switch SW1 connects to one of the output pins of the integrated circuit. When the voltage on that pin goes low, it causes a current to flow through the transistor base emitter junction, limited by the 27K, 2700 ohm resistor. This current causes the transistor to switch hard on, which in turn alters the voltage on its collector from near 0 volts to near 12 volts. The 27K resistor is only there to limit the current through the transistor and to avoid excessive loading on the output pin of the integrated circuit. The transistor now feeds current to the LED via the 21N4007 diodes and the 1K, 1000 ohm, resistor. This causes the light-emitting diode to light brightly. The 1K ILO ohm resistor is there to limit the amount of current flowing through the section of the circuit. Part of the voltage across the LED is fed back to the fuel computer. By moving the slider contact on the preset resistor VR2, any output voltage can be fed to the fuel computer. This voltage can be anything from the whole of the voltage across the LED, down to almost 0 volts. We will use VR2 to adjust the output voltage when we are setting the circuit up for use. In this circuit, VR2 is acting as a voltage divider and it is there to allow adjustment of the output voltage going from the circuit to the fuel computer. The final section of the circuit is the MPSA14 transistor and its associated components. This circuit is a timer. When the circuit is first powered up, by the vehicle's ignition key being turned, the 470 microfarad capacitor C1 is fully discharged. If it isn't, then the oxygen sensor will already be hot. As it is discharged and one side is connected to the plus 12 volt line, then the other side, point A, looks as if it is also at plus 12 volts. This provides a tiny current to the base emitter junction of the MPSA14 transistor, through the high resistance 470K, 470,000 ohm, resistor. The MPSA14 transistor has a very high gain and so this tiny current causes it to switch hard on, short-circuiting the LED and preventing any voltage developing across the LED. As time passes, the tiny current flowing through the MPSA14 transistor, along with the tiny current through the 3.9 megohm, 3,900,000 ohm, resistor R1, cause a voltage to build up on capacitor C1. This in turn, forces the voltage at point A lower and lower. Eventually, the voltage at point A gets so low that the MPSA14 transistor gets starved of current and it switches off, allowing the LED to light and the circuit to start supplying an output voltage to the fuel computer. The purpose of the section of the circuit is to shut off the output to the fuel computer until the oxygen sensor has reached its working temperature of 600 degrees Fahrenheit. It may be necessary to tailor this delay to your vehicle by altering the value of either R1 or C1. Increasing either or both will lengthen the delay, while reducing the value of either or both will shorten the delay. We want the time delay to occur if the engine is off for some time, but not to occur if the engine is switched off only briefly. For this to happen, it is suggested that a diode is placed across the timing resistor. This will have no effect when the circuit is powered up, but it will discharge the capacitor when the circuit is powered down. We can slow down the rate of discharge by putting a high-value resistor in series with the discharge diode, and that would make the circuit operation. Now that we have looked at each part of the circuit separately, let us look again at the way that the circuit operates. The main component is the LM3914 integrated circuit. This device is designed to light a row of light-emitting diodes, LEDs. The number of LEDs lit is proportional to the input voltage reaching it through its pin 5. In this circuit, the integrated circuit is used to provide a reduced voltage to be fed to the fuel computer, rather than to light a row of LEDs. When the operating switch is set in its on position, the sensor voltage is fed to pin 5 through a 1 megohm resistor. The sensitivity of this circuit is adjusted, so that when 500 millivolts, 0.5 volts, is applied to pin 5, the output on pin 10 is just triggered. This is done by adjusting the 10K linear preset resistor VR1 while placing a test voltage of 500 millivolts on pin 5. This LM3914 integrated circuit is normally switched so that it samples the sensor voltage. The LM3914 chip provides 10 separate output voltage levels, and the circuit is arranged so that any one of several of these can be selected by the rotary switch SW1. These output voltages range from 50 mV on pin 1 to 500 mV on pin 10, with each output position having a 50 mV greater output than its neighboring pin. This allows a wide range of control over the sensor feed pass to the fuel computer. The input resistor/capacitor circuit provides filtering of the sensor signal. Because this circuit draws very little current, it is easily knocked out of correct operation through its input line, picking up stray electrical pulses produced by the engine, particularly the vehicle's ignition circuit. When the exhaust sensor heats up, the signal becomes cleaner and then the circuit starts operating correctly. The circuit includes a delay so that after startup, the output is held low for a few minutes to simulate a cold sensor. The sensor must be operating correctly before we send signals to the computer. The most common problem, if we don't have this delay, is that the output will be high simply from the noise on the signal line. The computer will think the sensor is working, because it is high, and will cut back the fuel to make the signal go low. If that were to happen, we would end up with an over-lean fuel input to the engine, producing very poor acceleration. The front panel LED is not just to show that the device is operating, but forms a simple voltage regulator for the output signal to the computer. When the engine is warmed up and running normally, the LED is lit when the output is high, and not lit when the output is low, so this LED should be flashing on and off. The earth connection for the oxygen sensor is the exhaust system, which is firmly bolted to the engine. The computer earth is the vehicle body. A difference of just 0.5 volts can make a large difference to the mixture. If the engine is not securely earthed to the vehicle body, then a voltage difference can exist between the two, and in this situation a voltage difference of just 0.5 volts would normally go unnoticed. We can't afford to have that sort of voltage difference when trying to control the mixture accurately, so some investigation and adjustment is needed. To do this, start the engine, switch the headlights onto high beam, then measure the voltage between the engine and the body. Use a digital voltmeter. Any more than 50 millivolts, 0.05 volts, means that there is a bad earth connection which need cleaning and tightening. Modern cars usually have more than one connection, so look around. If you have trouble achieving a really good connection, then earth your circuit board directly on the engine rather than connecting it to a point on the bodywork of the vehicle. The most important item is to have a good quality signal voltage coming from the sensor, since the operating range consists of quite low voltages. The components and tools needed for building this circuit are shown later, but for now, consider the setting up and testing of the unit so as to understand better what is needed. Adjusting on the bench. When the circuit has been constructed to the testing stage, that is, with all components in place except for the timing capacitor C1, and before the power is turned on, plug the integrated circuit chip into its socket mounted on the board. Be very careful doing this as the chip can be destroyed by static electricity picked up by your body. Professionals wear an electrical earth wrist strap when handling these devices, so it would be a good idea to touch a good earth point such as a metal pipe cold water system just before handling the chip. It is vital that you install the integrated circuit chip the correct way round or it may be damaged. The circuit board layout shows which way round it goes. The chip has a semicircular indentation at one end to show which end is which, so be careful that the indentation is positioned as shown on the board layout in the section which shows how the board is built. Some manufacturers use a dot rather than a semicircular indentation to mark the end of the chip which has pin 1 in it. Make up the test voltage device. We need something to give us an adjustable voltage in the range 0 to 1 volt. A very easy way to get this is to use a 10 kilo ohm resistor and a 1 kilo ohm variable resistor, called a potentiometer by some people, and connect them across the 12-volt battery, as shown here. This gives us a voltage in the correct range when the shaft of the variable resistor is turned. Power up the circuit board by switching the 12-volt battery through to the board. Adjust the test voltage source to 500 mV, 0.5 volts, and apply it to the board's input, where the sensor connection will be made when it is installed in the vehicle. Set the switch to the richest position, that is, with the switch connected to pin 10 of the chip. Now, using a flat blade screwdriver, adjust the sensitivity control preset resistor VR1 so that the output LED is just lit. Leave the preset resistor in that position and adjust the test voltage lower and higher to test that the LED turns on and off in response to the varying voltage at the input to the circuit. The LED should come on at 0.5 volts, and go off just below 0.5 volts. The other outputs, which can be selected by the rotary switch SW1, will be about 50 mV lower for each position of the switch away from its richest setting on pin 10. Now, with the output high and the LED lit, use a flat-bladed screwdriver to adjust the preset resistor VR2 to set the output voltage being sent to the computer to about 1.0 volts. When this has been set, lower the input voltage so that the LED goes out. The output voltage should now be at 0 volts. If this is what happens, then it shows that the circuit is operating correctly. If this board is not in place, the sensor will cause the fuel computer to make the fuel mixture richer so as to maintain a 500 mV voltage from the sensor. With the circuit in place and set to its richest setting, exactly the same thing happens. However, if the rotary switch is moved to its next position, the fuel computer will maintain the fuel feed to maintain a 450 mV output, which is a leaner fuel-to-air mixture. One step further around and the fuel computer will make the mix even leaner to maintain a 400 mV output from the circuit board, which the fuel computer thinks is coming from the exhaust oxygen sensor. If your circuit board does not operate as described, then power it down and examine the circuit board again, looking for places where the solder connections are not perfect. There may be somewhere where the solder is bridging between two of the copper strips, or there may be a joint which looks as if it is not a good quality joint. If you find one, don't solder anywhere near the integrated circuit chip as the heat might damage the chip. If necessary, earth yourself again, remove the chip and put it back into the anti-static packaging it came in, before repairing the board. If the components are all correctly positioned, the copper tracks broken at all the right places and all solder joints looking good and well made, but the board still is not working correctly, then it is likely that the integrated circuit chip is defective and needs to be replaced. Next, install the delay capacitor C1. Set the test voltage above 500 mV and turn the power on again. It should take about 3 minutes for the LED to come on. If you want to shorten this delay, then change the timing resistor R1 for a resistor of a lower value. To lengthen the delay, replace the timing capacitor C1 with a capacitor of larger value. If you find that the oxygen sensor heats up quickly, then you can reduce the length of the delay. Having too long a delay is not ideal, since the computer will be adding extra fuel to make the mixture richer. It is suggested that the rotary switch should be set to have only 6 switch positions, by moving its end stop lug washer, so initially, connect the integrated circuit chip output pins 10 through 15 to the switch. You can choose to connect the wires to the switch so that the mixture gets richer when you turn the knob clockwise, or if you prefer, you can wire it in the reverse order so that the mixture gets richer when you turn the knob counterclockwise. Testing in the car. You can now test the device in the vehicle, but don't install it yet. Look in the engine compartment and locate the oxygen sensor. If you have difficulty in finding it, get a copy of the Climber or Haynes maintenance manual for your vehicle, as that will show you the position. If your vehicle has 2 sensors, then select the one nearest to the engine. If your sensor has 5 wires running to it, then it is a wideband sensor which measures both the oxygen content and the amount of unburnt fuel, and unfortunately, the type of circuit described here will not control it. Start the vehicle and allow the oxygen sensor to warm up for a couple of minutes. Remember that there is a delay built into the circuit, so after a few minutes you should see the LED start to flash. Rev the engine and the LED will stay on. When you release the throttle, the LED will go out for a while. A flashing LED is what you want to see. The rate of flashing will be somewhere between 1 and 10 times per second, most likely around 2 per second. Confirm that the LED goes out when you switch off the circuit board on-off switch mounted on the dashboard. Now comes the exciting bit, cutting the oxygen sensor wire and inserting the controller. Turn the engine off and cut the wire in a convenient place. Use crimp connectors on the wire ends. Use a matching pair on the wire which you just cut, in case you need to reconnect it, as shown here. When set up like this, the male connector furthest on the left could be plugged into the female connector furthest on the right and the circuit board removed. Be sure to insulate the sensor and fuel computer plug socket connections to make quite sure that neither of them can short circuit to any part of the body. There is no need to insulate the earth connection as it is already connected to the body of the vehicle. Although not shown in the diagram, you could also put a male and female crimp connector pair on the earth cable. If your sensor has only one wire coming from it, then your best earth connection is to a solder tag connector placed under a bolt on the engine. If you do that, be sure to clean all grease, dirt, rust, etc. off the underside of the bolt head and the area around the bolt hole. Push a paper towel into the bolt hole before doing this to make sure that no unwanted material ends up in the bolt hole, and use wet and dry paper to really clean the surfaces. The objective here is to make sure that there is a very good electrical connection with shiny metal faces clamped firmly together. Installing the controller. Now, install the circuit board in the vehicle. For the 12-volt supply, find a connection which is switched on and off by the vehicle's ignition switch. Don't drive the car yet, do this test in the driveway. With the front panel switch in its off position, start the car and check that it runs normally. Set the front panel rotary switch to the richest position, connected to the integrated circuit's pin 10, and switch the circuit board toggle switch to its on position. The car is now running with a modified oxygen sensor signal, although the mixture is still the same. The vehicle performance should be completely normal. Drive the vehicle with this setting for a while to prove that the system is working reliably before changing to any of the lower settings. When you are satisfied that everything is in order, Try the next leanest setting on the rotary switch and see how it runs. It is important that there should be no hesitation in the engine performance and no knocking or pinking, as that is an indication that the mix is too lean and the engine is liable to overheat. This circuit is intended for use with an electrolyzer, so your electrolyzer should be set up and working for these tests. The electrolyzer will tend to make the engine run cooler and offset any tendency towards overheating. Building the circuit board. Although the above information has been presented as if the board has already been built, the actual construction details have been left until now, so that you will already have an understanding of what the circuit is intended to do and how it is used. It is likely that you will know somebody, neighbor, friend, relative, who has the necessary equipment and skills. If so, borrow the equipment, or better still, recruit the person to help with the construction. It is very likely that anybody owning the equipment would be very interested in your project and more than willing to help out. However, the rest of this document will be written on the assumption that you cannot find anybody to help and have had to buy all of the necessary equipment. This project is not difficult to build, so you will almost certainly be successful straight off. The tools which you will need are: 1. A soldering iron with a fine conical tapering tip, probably 15 watts power rating. 2. Some multi-core resin solder. This is special solder for electronics construction work and is quite different from plumber's solder, which is not suitable for this job. 3. A pair of long-nosed pliers, for holding component wires when soldering them in place. 4. Something for cutting and cleaning wires and stripping off insulation coverings. I personally prefer a pair of nail scissors for this job. Others prefer a pair of wire cutters and some sandpaper. You get whatever you feel would be the best tool for doing these tasks. 5. A 1/8 inch, 3 mm, drill bit, for making bolt holes in the strip board and for breaking the copper strips where needed, and a 3/8 inch, 9 mm, drill and bit for mounting the switches on the plastic box. 6. A coping saw or similar small saw for cutting the rotary switch shaft to the optimum length. 7. A small screwdriver, for tightening knob grub screws. 8. A crimping tool and some crimp connectors. 9. A multimeter, preferably a digital one, with a DC voltage measuring range of 0 to 15 volts or so. 10. Optional, a magnifying glass of 4 times or higher magnification, for very close examination of the soldering. Soldering. Many electronic components can be damaged by the high temperatures they are subjected to when being soldered in place. I personally prefer to use a pair of long-nosed pliers to grip the component leads on the upper side of the board while making the solder joint on the underside of the board. The heat running up the component lead then gets diverted into the large volume of metal in the pair of pliers and the component is protected from excessive heat. On the same principle, I always use an integrated circuit socket when soldering a circuit board. That way, the heat has dissipated fully before the integrated circuit is plugged into the socket. It also has the advantage that the integrated circuit can be replaced without any difficulty should it become damaged. If you are using complementary metal oxide semiconductor integrated circuits in any construction, you need to avoid static electricity. Very high levels of voltage build up on your clothes through brushing against objects. This voltage is in the thousands of volts range. It can supply so little current that it does not bother you and you probably do not notice it. Complementary metal oxide semiconductor devices operate on such low amounts of current that they can very easily be damaged by your static electricity. Computer hardware professionals wear an earthing lead strapped to their wrists when handling complementary metal oxide semiconductor circuitry. There is no need for you to go that far. Complementary metal oxide semiconductor devices are supplied with their leads embedded in a conducting material. Leave them in the material until you are ready to plug them into the circuit and then only hold the plastic body of the case and do not touch any of the pins. Once in place in the circuit, the circuit components will prevent the buildup of static charges on the chip. Soldering is an easily acquired skill. Multi-cord solder is used for electronic circuit soldering. This solder wire has flux resin contained within it, and when melted on a metal surface, the flux removes the oxide layer on the metal, allowing a proper electrical and mechanical joint to be made. Consequently, it is important that the solder is placed on the joint area and the soldering iron placed on it when it is already in position. If this is done, the flux can clean the joint area and the joint will be good. If the solder is placed on the soldering iron and then the iron moved to the joint, the flux will have burnt away before the joint area is reached and the resulting joint will not be good. A good solder joint will have a smooth shiny surface, and pulling any wire going into the joint will have no effect as the wire is now solidly incorporated into the joint. Making a good solder joint takes about half a second and certainly not more than 1 second. You want to remove the soldering iron from the joint before an excessive amount of heat is run into the joint. It is recommended that a good mechanical joint be made before soldering when connecting a wire to some form of terminal. This is often not possible. The technique which I use is to stand the solder up on the workbench and bend the end so that it is sloping downwards towards me. The lead of the component to be soldered is placed in the hole in the strip board and gripped just above the board with long-nosed pliers. The board is turned upside down and the left thumb used to clamp the board against the pliers. The board and pliers are then moved underneath the solder and positioned so that the solder lies on the copper strip, touching the component lead. The right hand is now used to place the soldering iron briefly on the solder. This melts the solder on the joint, allowing the flux to clean the area and producing a good joint. After the joint is made, the board is still held with the pliers until the joint has cooled down. Nowadays, the holes in the strip board are only 1/10 inch, 2.5 mm, apart, and so the gaps between adjacent copper strips is very small indeed. If you solder carefully, there should be no problem. However, I would recommend that when the circuit board is completed, that you use a magnifying glass to examine the strip side of the board to make quite sure that everything is perfectly okay and that solder does not bridge between the copper strips anywhere. Before powering up the circuit, double check that all of the breaks in the copper strips have been made correctly. Here is a possible layout for the components on the strip board. If this board is turned over horizontally, the underside will look like this. This shows where the breaks in the copper strips need to be made using a 1/8 inch, 3 mm, drill bit. To construct this circuit, cut a piece of strip board which has 18 strips, each with 32 holes. That is a board size of about 2 inches, 50 mm, by just over 3 inches, 85 mm. Mount the components on the board, working from one end as the installation is easier if you have a clear board to work across. If you are right-handed, then start at the left-hand side of the board and work towards the right, installing all components as you go. If you are left-handed, then mount the components starting with the right-hand side of the board and working towards the left-hand side. Having said that, it is probably easier if you put all of the wire jumpers in place as the first step. The best wire for this is solid core wire of the type used in telephone wiring, as it is easy to cut, easy to remove the insulation, and it lies flat on the board, clear of all of the other holes. So, start with the wire jumpers and then install the electronic components working across the board. The jumper wires lie flat on the board, and like the other components, have about 2 mm of clean wire projecting through the copper strip before the solder joint is made. The wires coming off the board should be of the type which have several thin wires inside the insulation, as these are more flexible and withstand the vibration of a vehicle in motion, better than solid core wire. If you have just one reel of wire, then be sure to label the far end of each piece mounted on the board, the moment you have soldered it in place. These labels will help avoid errors when mounting in the case, if you do not have different colored wires. The completed circuit board can be mounted in a small plastic box of the type which has a lid held in place by screws. It may be convenient to screw or bolt the case to the underside of the dashboard and then screw the lid in place, covering the mounting screws. The components in this circuit are not critical and any near-match alternatives can be used. In the event that the MPSA14 Darlington pair transistor is not available, then two general-purpose high-gain silicon transistors like the BC109 or 2N2222A can be substituted. Just connect them like this. The emitter of the first transistor is connected to base of the second and the two collectors are connected together. If the transistors have metal cases, then make sure the emitter/base connection cannot touch either case as the cases are often connected internally to the collectors. If each transistor has a gain of only 200, then the pair will have a combined gain of 40,000 times. That means that the base current need only be 40,000 times less than the collector current of the second transistor. The BC327 transistor can be replaced by almost any other silicon PNP transistor in this circuit as the gain does not need to be great and the power rating is very small. The following is a list of the main electronic components needed for the construction of this circuit as described here. There are several suppliers who are able to supply all of these components and the most suitable depends on where you are located. If there is any difficulty, try an internet search, and if that fails, ask for help in one or more of the Yahoo enthusiast groups such as Watercar, Hydroxy or any of the electronics groups. Black plastic box with lid, size about 4x3x2. Strip board, 18 strips, 32 holes. Double pole double throw toggle switch. Fuse holder, panel mounting, 1.25. Fuse, 2 amps low blow 1.25. Rotary wafer switch, 12-way single pole. Knob for the rotary switch. LED, any color, 5 mm diameter. Integrated circuit socket, 18-pin DIL. Miniature preset resistor, 10 kΩ linear. LM3914 LED bar driver integrated circuit. BC327 PNP transistor. MPSA14 Darlington pair transistor. 1N4007 diode or equivalent. BZX85C Zener diode, 24 volt version. 470 microfarad, 35 volt, or higher, axial lead aluminium foil electrolytic capacitor. 100 microfarad, 35 volt, or higher, axial lead aluminium foil electrolytic capacitor. 100 nanofarad, 0.1 microfarad, ceramic disc capacitor. 10 megohm 1/4 watt carbon resistor. 1 Radio Shack 271-1365, 5-pack. 1 megohm 1/4 watt carbon resistor. 470 kilo ohm 1/4 watt carbon resistor. Use 2 1M in parallel or 271-1133, 5-pack 1/2 watt. 10 kilo ohm 1/4 watt carbon resistor. 2.7 kilo ohm 1/4 watt carbon resistor. 3.3 kilo ohm 1 kilo ohm 1/4 watt carbon resistor. 100 ohm 1/4 watt carbon resistor. Connecting wire, stranded and solid core. Electronics Express http://www.lexp.com/index.htm. Radio Shack http://www.radioshack.com/home/index.jsp. And for a UK supplier. Black plastic box with lid, size about 4x3x2. Strip board, 18 strips, 32 holes. Double pole double throw toggle switch. Fuse holder, panel mounting 31 mm. Fuse, 2 amp 31 mm. Rotary wafer switch, 12-way single pole. Knob for the rotary switch. LED, any color, 5 mm diameter. Integrated circuit socket, 18-pin DIL. Miniature preset resistor, 10K linear. LM3914 LED bar driver integrated circuit. BC327 PNP transistor. MPSA14 Darlington pair transistor. 1N4007 diode or equivalent. BZX85C Zener diode, 24 volt version. 470 microfarad, 35 volt, or higher, axial lead. Aluminium foil electrolytic capacitor. 100 microfarad, 35 volt, or higher, axial lead. Aluminium foil electrolytic capacitor. 100 nanofarad, 0.1 microfarad, ceramic disc capacitor. 10 megohm 1/4 watt carbon resistor. 1 megohm 1/4 watt carbon resistor. 470 kilo ohm 1/4 watt carbon resistor. 10 kilo ohm 1/4 watt carbon resistor. 2.7 kilo ohm 1/4 watt carbon resistor. 1 kilo ohm 1/4 watt carbon resistor. 100 ohm 1/4 watt carbon resistor. Reel of multi-strand connecting wire 6 amp red. Reel of multi-strand connecting wire 6 amp blue. Reel of solid core, or local phone wire. While the components listed above are the parts needed to construct the electronics board, the following items may be needed in addition when testing and installing the board in a vehicle. Rubber or plastic grommets to protect wires from rubbing against the edges of the holes in the box. Crimp bullet connectors male and female, 1 pair for each sensor wire cut. Mounting bolts, nuts and spacers to hold the circuit board securely, clear of the box. Double-sided adhesive tape for mounting the box on the dash. Alternatively, hardware items for this. Fuse box connector for connecting to the fuse box to give an ignition switch 12-volt supply. 10 kilo ohm resistor and 1 kilo ohm linear variable resistor for bench testing with voltages of up to 1 volt, if these components are not already to hand. Multimeter for general checking of voltages, continuity, etc. I should like to express my sincere thanks to the various members of the Watercar Group who provided the technical information and patient support which made this document possible. An alternative, as the signal coming from the oxygen sensor to the vehicle's ECU fuel computer needs to be raised slightly to allow for the much cleaner exhaust produced when a booster is being used, an alternative solution has been suggested and tested. The idea is to add a small, adjustable voltage to the signal already coming from the oxygen sensor. This voltage can be from a single dry cell battery and adjusted with a variable resistor. The circuit shown here allows a voltage anywhere from 0 to 0.5 volts to be added to the oxygen sensor signal. This must not be done unless a booster is running. Using it without a booster is liable to lead to engine overheating and possible valve damage. This, of course, applies to the previous oxygen sensor signal adjusting circuit as well.